mood lighting. Oh, that's better. So y'all handled one of these. Yeah, go ahead.
Tyler just messaged me. He said his car broke down.
I hate hearing that. That's too bad. All right, I'll just mark him down as a late for now. So you all held one of these in your hand when you took your engine apart, right? Push the piston pin out, put the piston pin back in it, put it up on the stand. Okay, so this next week or tomorrow, I want you to really look at these things and kind of make sure that your mind agrees with what you're seeing, that what you have in your hand. Now that's a pretty big piston there out of a pretty big engine. It's got a lot of grooves cut in it for a lot of piston rings. I think yours probably have 3 rings on it, and that's about the extent of it. Maybe some of the bigger engines have 4 rings on it.
Is the hole a wrist pin?
What's that?
Is that what a wrist pin is? The hole?
The big hole, yeah.
Okay.
All right, so you know that the piston's going to move back and forth. It just moves in a linear movement. Doesn't have any oscillation, any turning to it. It goes out, stops, comes back, stops, out, stops, back, stops. And it has a high speed point. The highest speed that it travels is about halfway through its piston movement between top and bottom center. That's the highest speed that it ever attains. The slowest speed is when it comes to a grinding halt. Well, hopefully it doesn't come to a grinding halt, but it comes to a halt at the top and the bottom of its travel, and then it reverses direction. So it does momentarily come to a complete stop. So what we're going to do is we're going to convert that expanding combustion gas. We're going to take that heat and that gas, that expanding gas, and turn it into a linear motion. We're then going to transmit it through the connecting rod via the pin, the wrist pin, okay, or the piston pin. It can be known as a couple different things. So you can walk them right to both of those down. Connecting rod is attached to the piston with the piston pin, okay, or the wrist pin is another name for it. Okay. Wrist pin, because it acts like this on the piston. It's known as a wrist pin. So between the piston moving just in linear motion, and you have the crankshaft turning in a circular motion, you have the connecting rod moving through an angular motion to connect the piston to the crankshaft. And I think you can all see that now. If you think back last week when you took your engines apart, you'll see how that works. Now the pistons aren't what actually does the sealing. It's the rings on the piston that do the sealing. So the cylinders, the clearance between the cylinder and the piston are going to be between 3 and 8 thousandths of an inch. So it's still fairly close fit, but it's a nice loose fit. So remember, when the cylinder gets hot, what happens to the diameter of the cylinder?
Expands.
Grows, right? It grows. And so what are we confident that's going to happen with the piston when it gets hot? What's going to happen to that piston diameter when it gets hot? So it's going to grow out and follow the cylinder, right? Same. So we have up to some pretty great clearances here. And if you figured that was all the way around that piston, without any piston rings, there'd be a lot of gas escaping past that. So we add the rings to do the sealing because they're compressible. And they will hold a tight clearance up against the cylinder walls and keep that gas on one side, and we'll keep the oil on the other side. We don't want the gas escaping past the piston. Pistons themselves are pretty simple. The rings is what start complicating things. And then once again, piston pins or the wrist pins, either known as either way, wrist pins or piston pins, they attach the piston to the connecting rod. How many of you, the wrist pins came out hard on your engines? You had to really push and shove on. Which one are you working on, Dee?
The one that just.
The what?
The one that you just brought back from Montgomery.
Oh, yeah, okay,
one from
yeah,
South
that one has come out of service. It was on a Beechcraft Traveler. And it was, the Traveler was given to the school and they filleted it out into little pieces, so it has never been taken apart as long as the school has owned this thing. So what you end up with is you start looking at the clearances on this stuff. On a wrist pin, it's only about 1.5 thousandths of an inch of clearance for that piston pin to slide in there. So most of you know your piston pin slid through the piston pretty easily. Maybe a little bit sticky, but went through. You could push it with your thumb. Hers didn't because it had a little ring of carbon on it. Just a little bit of a ring of carbon filled that clearance up to where the thing didn't want to come out. I heard about that. That's pretty typical. Okay. So we use a couple of rings for compression control, and then we're going to have what we call an oil control ring. Oil control rings. So remember, where's that big piston at? Where's that big piston? Okay, so you got it back there. If you all look up inside of that thing, you remember, up inside of it, there's a bunch of cooling fins inside there. We're going to use the oil, which is, we'll say 200 degrees, just for nice round numbers. Nice round numbers. So what we're going to do is we're going to be carrying a lot of the heat away off the top of this piston here from the oil that we're going to spray on the other side of it. Now, there's going to be some splash oil in there. Most every engine has splash oil lubrication underneath the piston, but a lot of them have a dedicated spray path of oil to help carry some of that heat away. And you start finding that in higher compression engines where the temperatures are even higher. So pistons come in a lot of different shapes. They also come in standard and oversized diameters, and they also come in different weights. There's a lot of different ways that you can get pistons. So if you're overhauling an engine, you try to get a set of pistons with all about the same weight. That way your reciprocating weight is about all the same between all the cylinders, and that cuts down on the vibration. Okay. Now they're not going to be dramatically different as a set, but you have to know that when a piston is fabricated and metal is cut off of it, there are going to be densities in the metal. Some places will be more dense than others, and so you could end up with a piston that's going to be several grams more on one piston versus another piston. So you end up with lighter weight pistons and heavier weight pistons. So try to get them all in a match set. The other thing too is when you go to replace just one, you can order them by weight. They just order them by weight individually, and most of the time the parts houses have them by weight. Okay. So here's the basic shape of the piston. Now, not all pistons are shaped like this on the tops, but generally speaking, from here down, they're all pretty much the same. There are some clearances that are cut into them. Sometimes they're just cylindrical shape, like that one on the top up there on the right. The piston has what is known as straight cut skirts. So let me hold one up. It's not straight cut. You see the difference in those two there? Okay, so this lower part down here is called the skirt. This is also the skirt on this one. See the difference in those skirts? Okay. Now the reason is this one doesn't have that cut in it is because the piston doesn't go down so far into the cylinder that it's going to get near the crankshaft. This one goes down into the cylinder quite a long ways toward the bottom, where the crankshaft counterweights would strike it otherwise. So what they do is they take some weight out of the piston, two things. They take some weight out of the piston, but they also cut this clearance in there so the crankshaft doesn't strike the piston when the piston comes down. Does that make sense? Yeah, that's why they do that most often. Sometimes it's just to take weight out of the piston. Anything that has less weight in it is gonna reciprocate a lot faster because there's less mass. So you're gonna have the piston pin. Piston pin fits through this boss, which is this hole right here. This is the piston pin boss. Actually, this whole area right here is the boss in the piston. So when you go to take a measurement, you're gonna measure through the bore here. You're gonna measure it for a diameter. You do the same thing over on this side. And you're gonna bump that number against the diameter of the piston pin. And that's gonna give you the clearance between the two. Okay? Yeah, that's gonna be one of the clearances you're gonna be taking. So you're gonna be looking for a worst case scenario. So this is aluminum. Your wrist pin is gonna be steel, hardened in ground. Hardly ever do you get much wear on the wrist pin. Where you're gonna find it is gonna be in the aluminum here. So remember, this piston goes out, has a little bit of weight, you all know what it weighs now. When it goes out, it does a complete stop, and then it tries to go the other direction. Complete stop, back and forth, back and forth. And so where would you guess, as you're looking at this right now, where would you expect the greatest amount of wear on this clock position? We have clock position in this hole here, 2 clock positions. Where is going to be the greatest amount of wear in this hole, as you see the way you see it sitting here right now?
12 and 6.
What's that?
12 and 6.
12 and 6. And 12 and 6 why?
Because those are basically the points that the pin is using to actually stop the piston head from going either out or in.
Right. So you're decelerating mass or accelerating mass in those 2 clock positions on this. So so this thing is moving. The piston pin is trying to retain it going this way, and then the piston pin is slamming against it the other way. It's not really any slam because the clearances are so tight. There's not much movement there. But eventually, if you have any wear, that's where you're going to find it, worst case scenario. So when you measure this stuff, anytime you have a diameter that you have to measure or a bore, in this case, the piston, you're going to look for it here and here. You take 3 measurements, right? Take one here, take one here, and one here. You can take more if you want. Oops, it's 2, 3, and not in any particular order, but you're going to expect to find a major amount of wear between the 2 ones. Does that make sense to you? Okay. So anytime you're doing any kind of wear assessment, this wouldn't be surprising to find more wear across this axis here than it would be across the other 2.
Is that something you can hear or no? I mean,
Clanking, some kind of looseness, you mean?
yeah, like,
In an extreme case, I guess you could.
Yeah.
But usually what happens is you have what they call piston slap. And piston slap is caused because the rings start wearing out. So the rings also support the piston. They don't only seal the piston, but they support the piston. And so you can imagine when the piston goes up and when the piston goes back, it changes direction with the connecting rod pulling on it. I don't know if this connecting rod goes with this or not, but let's say the connecting rod is in this position here. So this thing goes out like this, and then it changes direction. The connecting rod's going like this. So the piston tries to slap back and forth. And when it tries to cock itself in the cylinder, there's not much clearance. So it doesn't move very far. And so you end up with what they call piston slap, and that's the skirt. This part right here, striking the cylinder wall. Already got that piston slap. So it's the piston tipping back and forth. And you'll hear that before you'll hear any looseness in the rod on the piston itself. All right, so there's another type here, slipper type. It can be a flat top piston. That's this one right here. But what it is it has the skirt has been cut out of it to lighten it significantly. And I don't have one of those here, I don't think. Yeah, I don't have one of those here. But what they do is they just take a lot of metal out of this, in this area down in here, and it just lightens it up. Now, another type, so this is slipper type, it's kind of a flat top piston. Then you're gonna have a trunk style. The trunk style has a full solid head on it. It's like this one here. Okay. So this has got, in this case, this is a trunk style flathead piston. It's got a pretty much square shape to it, nothing too tricky. This is what you have in your engines. You might also have a recessed head. Got a flat one here, recessed, yeah. Got one here. You might also have a recessed head. You see the, I'll put this up here. You see the little cutouts in this flathead piston here? These two cutouts are for the valves, so the valves don't strike the tops of the pistons. So when the piston comes up, the valves are still open slightly, right? And those valves will close, as this thing moves up, the valves will close just ahead of this. But when it does, you don't want this piston to strike those valves. If the piston strikes the valve, you end up with this. All right, you don't want that to happen. Okay. Or you end up with this. You don't want that to happen. So it gives a little cutout in the top. There may also be one that has a dish in the top of the head of the piston, like this. Might have a dish in the top of the head. You see more of these in diesel type or very high compression engines. And what they'll do is they can change the compression ratio on the engine by giving a little bit more combustion space. So if your combustion chamber is a little bit on the small side and the compression ratio is a little bit too high, they can just take a little bit out of the piston, and then what that does then is it gives you more compression space, and so it lowers the compression ratio. So let's say, and how this relates to the engines is if you have a turbocharger or a supercharger. It pushes air into the cylinder instead of having it drawn in. And when that happens, when you push it in, you compress it. What happens to your temperature when you compress it?
Increases.
Temperature's going to increase. All you would go along with that in the back there. Okay, good. So, so it's going to increase the temperature of the air. Now, what happens when you put fuel, discharged fuel, into hot air? There's a very good chance you could end up with a spontaneous combustion or a diesel effect. Okay. Now, if that occurs, and we call that what? In a gasoline engine, what do we call it?
Combustion.
So we call it detonation. Right? So detonation is not a good thing because if it starts detonating, it doesn't give the fuel enough time to burn. I showed you the picture of the fuel burning across the flame front. Well, that doesn't happen with detonation. It all just goes off at once. Instead of having a flame front, it's just an explosion. So what happens to the piston? So I've got one here. I don't have one here. What happens to the piston, the top of the piston, when that temperature rises so rapidly and the piston is still coming up? What happens to it? Somebody heard I heard the word back there. Somebody back in the back. Somebody back in the middle. So the piston's still coming up. It's almost all the way to the top, and this thing starts a combustion. What's going to happen to the piston? It's going to be a shock. Shock wave is going to occur. It's going to drive it right through the piston. You can end up breaking a piston real easily, but probably what will happen is you'll end up burning the edge off of it, like this. So the temperature is going to get pretty high on top of that piston, and it's going to burn off the thinnest part of the piston. It's going to melt that off, and that's just going to be metal that's coming off the piston. So this thing eventually will break. In this case, I'll put it back up here so you can see. But in this case, what it started doing was it started melting the edge off, and it finally burned a hole through the piston. So what happened to the compression on this cylinder? Right in the toilet. So now the gas that was created in this cylinder, if you can see it burned a hole through this, where did that gas go? Into the crankcase. Into the crankcase. When it goes into the crankcase, So the crankcase is a breather.
Sure.
We're gonna be dumping that combustion gas overboard. And that combustion gas overboard is also gonna carry oil with it. Or it could be setting the oil on fire inside the crankcase, so you could end up with an engine fire also. There's a number of different possibilities, so you don't want that to occur.
How does something like that happen in the first place, where you'd have the wrong
Starts to happen, yeah.
seriously?
Something precipitates that. It doesn't just happen. Okay. So combustion, detonation. So we can do it artificially with a supercharger. The air temperature gets too high. So maybe it works perfect, and then maybe one day you go over to Phoenix and it's 115 or 120 over there. Most of the time it's 100 degrees someplace tops. But now you add that extra 20 degrees to it. Is the air temperature inside the engine going to be 20 degrees hotter with a supercharger?
Sure.
Sure it is. It's going to take the ambient air temperature and raise it up whatever that extra few degrees is. That may be the thing that precipitates the detonation. High air temperatures is a good thing, a good reason for that to occur. So as soon as you introduce fuel into the high air temp, it just explodes rather than burning. So we haven't even had the chance to combust it yet. And the piston is still going up. As that piston starts going up, there's something pushing it back the other way. Now you can end up with a connecting rod that's not happy with it. You can end up with this. This is supposed to be straight. It's supposed to look like this. So that's connecting rods can also get bent by having the engine try to run backwards. Let's move on. Okay, so you have truck side, which is it's got straight sides, and it's transitioned into a skirt area. So it may not have this cut, which is called a recessed skirt. It may or may not have this cut in it. A slipper type, this is a somewhat more pronounced cut, and some of them have very small cuts in here. So this is going to give you room. It's going to do two things. One is it may just lighten the piston, because these pistons are kind of heavy by any standard. But the other thing that it might do is going to give you clearance on the crankshaft. As you turn the crankshaft, the counterweights will slide right past these. Then there won't be any obstruction. Okay, so here's a recessed top piston here. I think I was just showing you one of those. Maybe a little bit hard to see, but there's some cutouts in here for the valves to go down. As the valves are down, the piston's coming up. The valves are also coming up at the same time, and so we don't want to have any connectivity between the valves and the tops of the pistons. Okay, so here's a cutout here. These are two valves that sit side by side instead of being diametrically opposite to each other. These two valves here and one here does the same thing, and that's why the cutout is in the top of that head. Okay, it's also slipper type. It's been cut away at the bottom quite a lot, and that's going to take a lot of weight out of this piston here. Okay, the piston body itself. Just back up here real quick, because I can do this. I can help you out with this just a little bit. It's a good picture here. So when I start talking about rings, grooves, and ring lands, the grooves are pretty apparent. Those are these grooves that are cut into the piston, as the name implies. Anything that is a high spot is called a land. Okay, this thing has three lands on it. And think of island or land or however you want to do it. So there's the grooves, and then you have the lands here. Now, when things get hot, what's gonna burn off first? What's gonna melt away first? What's that?
The land?
The lands, because the lands stick out, they're kind of thin cross sections. They're exposed to the heat, especially the top land up there. And that piston here again. There it is here. So if you take a look at this thing, it started at the top. That hot gas started melting it away and finally just melted right through the next land, the next land, and the next land. The bottom of the grooves of the piston itself were pretty much unobstructed until it connected and had a path to flow through. Okay, so you've got that hot gas, about 2,500 degrees. Will 2,500 degrees melt a piston? You betcha. It'll melt aluminum, no sweat. So, so what you want to do is you want to make sure that you're sucking the heat away from the bottom side of this, but also you don't allow any part of this piston to get too hot or you end up losing it. Okay, so let's move on to the next. Okay, so the compression rings. You're gonna have a piston body. You're gonna have compression rings. You could have 4 piston rings. Most modern engines have between 1 and 3, but you could have 4. Then you're gonna have oil control rings. Now the piston rings, or the compression rings, are different than the oil control rings. So the oil control rings are gonna do a couple of things. They're gonna carry the oil up, they're gonna wipe the oil up, and they're gonna carry the oil back down away from the top of the cylinder. So they're gonna lubricate the movement of the piston rings going up into the cylinder, up towards the combustion chamber, and then another ring is gonna draw it off like a squeegee and pull it back into the engine when the piston moves down. Because you don't want that oil laying up there. If it lays up there, it'll get pumped up into the combustion chamber, and then where does the oil go once it's pumped into the oil into the combustion chamber? Where does it go?
Exhaust.
Goes out through the exhaust, and then what happens? So look at the back. You get 2 compressors back there. Where does that oil go? It goes out the exhaust. It's going to go past the spark plug. Is that going to have any effect on the spark plug? Let these guys back there. They'll get too comfortable. It's just that. What's going to happen to that oil that is being carried into the combustion chamber? Yep. We don't want extra oil in the combustion chamber. Okay, so we got spark plugs in the combustion chamber. Would oil have any effect on the spark plug? And I'm gonna let you answer.
I have no idea.
So let's go this way with it. So you have a gap, an electrode gap in the spark plug, right? And if the spark plug begins to consume or has to deal with too much oil, what can happen to the gap in that spark plug? We need to have that gap occur so that we can get a spark, right? With electricity, you gotta jump that gap to make a spark. And it's the same with a turbine engine. You still gotta have a gap up there at the top of that plug. And if we start burning oil in the top of the cylinder, what's gonna happen to that gap on that electrode? There's gonna be no gap, and then what happens? What's the next step that's gonna happen? No ignition, okay? So now you've got a dead spark plug. Would you agree with that, right? Yeah, so now you got a dead spark plug, and you got a dead spark plug now. Now what happens is that oil, what's left of that oil is gonna go overboard. It's gonna be in the exhaust pipe. It'll be on the belly of the airplane probably. but you've got less ignition going on in one cylinder than you do all the other cylinders, and maybe they're all in the same shape. So you've got two magnetos. Now for that cylinder, you only got one magneto operating, right? And so the engine's gonna run smoothly or less smoothly. Will it even matter? You're still on the hook.
I don't know, I'm here to learn this, I don't know.
Yeah, that's what we're trying to get you to do here. And this is the best way to learn it. So think about this, and the rest of you think about this too. I'm not just picking on him, because I'll pick on all of you eventually. And so now you've got basically one dead magneto. The magneto's firing fine, but it's not causing a spark to occur in that cylinder on that spark plug. The other spark plug is going to fire, and so the cylinder will still continue to run. We know, I don't know if you've been in a place where you've been able to run an engine yet. Have you had Recips 2 yet?
No.
No? Okay, so here's what happens. When we do a magneto check, we shut off one magneto and we're going to lose some RPM. Then we go back to both. And then the RPM picks up, usually about 150 RPM, something like that. And then we go back to the other magneto, and this is what we're doing, we're causing a magneto check. And then the RPM will drop, because what we're doing is we're shutting off one magneto at a time, and we're just verifying that both magnetos are working. So if now the aircraft's in flight, and we start losing RPM, because we have a fouled spark plug, would you guess that the engine, and just make a guess, would you guess the engine is going to run a little rougher, or they're going to run the same?
Rougher.
Probably just a little bit rougher. Okay. But what's going to happen to the fuel economy of this engine? It's going to go down, right? So it goes down. Okay. The fuel economy is going to get worse. Go back to Mr. Stafford. And so we'll finish this and go to the final conclusion here. And so we have multi-point sensing on this engine. And we have cylinder head temperature, which should run about 350 degrees, so it's a nice long number. And the exhaust gas temperature, that is to say that the temperature of the gas in the exhaust pipe is now going to run about 1500 degrees ordinarily. What will happen if that cylinder, that particular cylinder, is now got one dead spark plug in it, and it was running at, CHT was 350. Oops, 350. And the EGT, exhaust gas temperature, was about 1500 degrees. What will happen to those two temperatures? You don't have to tell me the degrees, but what will happen to the CHT and the EGT as a result of that spark plug not firing? What would you think? Just take a swing at it. What's that?
The lower.
So which one will go lower, or both will go lower? Both go lower? You're close.
The EGT go
And
first.
here's why. Because now you're not creating the power out of the cylinder head that you were before, because you have one dead spark plug. Would you all agree with that?
Yes.
So the power is down. So the cylinder head temp will probably go down a little bit. But that fuel that would ordinarily be burned in the cylinder, where's it gonna go? Where?
Exhaust.
Where?
Exhaust.
Exhaust. Okay, so it's gonna head into the exhaust, but it will continue to burn, knowing that the valve is gonna, as soon as that piston gets to the top and the piston starts going back down a little bit, it gets down about 3/4 of the way. What happens to that valve in that cylinder? The exhaust valve. It opens. It begins to open. And so you've still got fuel burning in that cylinder, and so what's gonna happen is the EGT is gonna climb slightly. because now you've got burning fuel in the exhaust pipe. Okay, so all of this, and I'm not picking on you, but, so you did pretty good. For knowing what you know. And the rest of you, I'm gonna pick on you all, get your chance, because we got plenty of days left here. So know that the CHP is gonna drop a little bit, and the EGT is gonna rise a little bit, because we're not keeping all that gas in the combustion chamber, it's getting out, it's getting into the exhaust pipe. And you have to have multi-point sampling on the temperature to be able to see this. A lot of engines only have one EGT and one CHP, and you're never gonna know unless it happens on that one cylinder. So most everything now is multi-point sampling on temperatures. But this can be a huge way to see what's going on inside the engine, a good way to know. Back to the rings. So the wiper ring allows oil to be carried up the cylinder wall. So last week I showed you the cross-hatching in the cylinders, how that's got all those minute little scrapes in there. And if it's chrome, it looks like crazing in there. All that holds oil. Well, when the ring comes back, the piston comes back down, it has a squeegee effect on it. It pulls that oil back into the crankcase and just goes into the crankcase, goes back into the sump, and then it's recycled again. Okay. Piston heads. So we talked about that. But I'll let you write that down or get a picture of that if you want.
Okay, so you're saying that a wiper ring will bring the oil up and down up the cylinder, but a scraper will bring it.
Wiper will carry it up and a scraper will drag it back down. Now they can be the same ring, but most ordinarily there's two rings. One performs one function, one performs the other.
Is there a normal stagger on that, or is
Yeah,
it?
I'll show you what that is.
Okay.
Yeah, we're gonna talk about rings here quite a bit. Most of the small aircraft engines, recips, you're gonna see are gonna have the first three there. Some of them will have a interference recess for the valves, but the truncated and flow controls are mostly older airplanes, older big engines, and so you probably won't see too many of those floating around. Okay, so the ring grooves, the ring lands, I showed you those. The oil control relief holes. So when you look at the piston, I may have a picture coming up here, but I want you to see there are holes drilled in this piston. Here and here and here and here. You'll see those holes kind of hard from the back probably. But there are a bunch of holes drilled in this piston. And you'll see this in yours too. You may not have so many holes. I'll bring this piston back and then let you all pass it around again. What those holes do is they give the oil some place to go to when those wipers and scraper rings are working. So they allow the oil to pass through the skirt of the piston back into the inside of the piston. So they're going to help carry some of that hot oil off the cylinder walls. When it comes off the cylinder walls, it's going to carry some heat with it, and then it's going to go back into the crankcase or the sump. And you got the piston pin. So the piston pin, you got the caps and the retainer, some way to keep that pin from floating back and forth. What did you have on all your engines anyway? Caps?
Small, little caps.
Yeah, little aluminum caps. Ordinarily, they work pretty good because they just float in the piston back and forth, they bump the cylinder wall, they just go the other way, no big deal. They just touch lightly, they're aluminum, if anything wears off, it's no big deal, just goes into the crankcase, and it's just consumed in the engine. Okay, and then the pin boss, so I showed you all the pin boss, right? It's that part that supports the hole for the wrist pin. Skirts, you might have cooling fins in it, like that one that's floating around back there. You got piston skirts and the cooling fins. Let me show you. So you all saw that one that's floating around. Here's a different kind of cooling fin here. If you look up inside there, it looks like a waffle. Okay, so we're gonna hit the top of this head, piston head, with oil, and those cooling fins are gonna give us more area to carry the heat away from. This is gonna help carry the heat away off the top of this piston here, just by virtue of the shape. So we've added a lot of square area here. We'll just spray that with oil. When that oil comes off, it's gonna carry a lot of that heat with it. So piston body is the main structure of the piston. Most all of them are made from aluminum anymore. They can be cast aluminum. They can be forged and stamped into shape. A couple of different ways to do it. So they shape them out rough to begin with, then they're machined to shape. So they cut the sides clean. They cut the sides and the tops. Most ordinarily, there isn't much machine work that goes on the inside because of the difficulty of getting inside these things. Now, a lot of times when they put them on a lathe, you're going to find there's a little point. I don't know if you'll see this on your pistons or not. You see that mark right there? It's a little center point in there. And they use that as a reference on the piston to keep it centered when they cut it. So there's a center point goes on it. They turn this in a lathe and cut the outside diameter off. So that's what keeps it from flopping around while the machining operation is going on. So if you see that centering point, it's not somebody hit it with a center punch. It's a center point from the manufacturer of the piston. Now the sides, they might be what they call cam ground for thermal relief. Now, when the piston, I asked you this earlier, think about this. When the piston starts getting hot, what part of the piston is going to grow the biggest, the fastest? Is it going to be this part in here, or is it going to be this part in here and this part in here? What part's going to be the most thermally stable? It'll be this. We'll call it 3 and 9, or is it going to be 12 and 6?
3 and 9.
3 and 9 is going to crawl around the most, and that's because it's a thinner part. So aluminum grows and has a great reactivity to temperature. So when things get hot, it starts moving pretty quick. The thicker parts, like anything, so you all ground your drill bits over here on the grinders, right? And so you ground it, and it got red hot. Pretty soon you couldn't hold the damn thing anymore, right? Because it was such a little part. But if you're grinding some really big chunk of steel, does it get so hot so quick that you can't hang on to it? No. And so think about that. So the part that is the thickest is going to be the most dimensionally stable part. So what they do is they do what they call a cam grind on. What that means is it's going to actually be an oval shape. So if you take the piston, all right, if you take the piston, this is exaggerating it. So you've got the bosses inside. It's going to be actually a little bit oval shaped. Okay, so the pin's going to go through here. It's going to start out the biggest on that side there, And it's gonna be the narrowest in this, through this section here. Because as this expands, what's gonna happen to the shape of the piston? So we start out with it oblong, what's it gonna do when it gets hot?
Go concentric.
It's gonna go concentric or round, right? This part here is gonna grow the fastest, and so it's gonna move this way. And this one is also gonna do the same thing. So you'll end up with a concentric or a round piston once this starts growing along this edge here. Does that make sense? So concentric is a word you're gonna hear in here a lot. Concentric means that it's gonna be round. If you don't know what that word means, you write it down.
So it's starting already kind of,
Starting kind of oval.
right,
Yeah,
and
you
then-
take it out of the box, it's gonna be a little bit oval. Now, this is a kind of an exaggeration. It may only be like 4 or 5 thousandths out of round. Okay, so when you measure your pistons, you may find that you're gonna have one measurement across 180-degree stretch is gonna be out of round or smaller, and that's gonna be a cam ground piston, more likely than not. Okay, so the sides may be choke cut. Remember choke in a cylinder? What was that all about? Mr. Kepke, what was that all about? Choke in a cylinder. Remember we have more choke in the top of the cylinder? What was that all about? So choke was, what we do is we grind the cylinder. So you would think that the walls of the cylinder would be parallel with each other. But when we grind the cylinder, we actually have it just a little bit tighter at the top, a few thousandths tighter at the top. So what happens to the diameter when it gets hot? It's going to grow. So if the barrel has a choke in it of 5 thousandths of an inch or 6 thousandths of an inch, that means that each wall is 3 thousandths of an inch closer at the top than it is at the bottom. Okay, go on with that. And so when this reaches operating temperature, what does that do to the parallelism of the walls of the cylinder? It's going to straighten it out. Okay, so if we do that with a piston, at the top of the piston, if we tighten it up just a little bit at the top of the piston, if it's a little smaller up here, all the way around, than it is down here, what's that going to do to the shape of the piston when it gets hot at operating temperature?
Does it allow the top to become like a vector?
Exactly right. So the walls of the piston or the sides of the piston are going to become parallel. So the reason for that is now all your clearances are going to be the same all the way through the engine once it reaches operating temperature. Now this is something that really has as much to do with air-cooled engines as it does anything. Air-cooled engines, because when you take off, you're generating a lot of heat. When you get at cruise, the temperature is pretty stable. But when you tip the nose over on the airplane, you have a lot of cold air rushing into the cowling. What happens in the engine, temperature-wise? It's going to go down, right? And when that temperature goes down, what happens to the shape of the engine?
Changes.
It goes back to oval.
It's going to change, right? It's not going to go back to normal, hopefully, because your engine's still running, making a little heat, right? So, so the length of the engine is going to do what?
contract.
It's going to contract. The width of the engine going to contract. The cylinder size is going to contract slightly, and that's why in an air-cooled engine we have to have big clearances on everything, because you have all of these three dynamics working on the engine. You take off, you're generating a ton of heat. Once you get up, it's pretty temperature stable, and then once you tip the nose over, it starts cooling down quite a bit. So you have to be able to encompass all these extremes. So if you have let's say 5 thousandths of an inch clearance on the piston into the cylinder, the fit is 5 thousandths of an inch. So that means you have 2.5 thousandths on each side of that piston, right? 2.5 thousandths on each side of that. That's nothing. When you hold your fingers up, you can't even see between your fingers for 2.5 thousandths. It's pretty darn close. And so you tip the nose on the airplane over, what's going to happen to the shape of the barrel? Well, the piston's gonna lag behind a little bit because you still got power on, you're still gonna keep heat on. So you have to have pretty big clearances to allow that piston to still run in the cylinder without rubbing on the cylinder. If it rubs on the cylinder, you're gonna have a bad event about to happen. That's why you have to have plenty of clearance in there. Okay, so the pin boss, that's the heavy part of the piston. We're gonna bore through it horizontally. We're gonna cut the ring grooves. They're cut into the piston itself, and that's gonna create the ring lands. So the ring lands ordinarily are the same diameter as the skirt. When you measure around your pistons, after you take your rings off, you're gonna measure probably 3 times, 3 places, and where you measure doesn't matter so much. But you're gonna measure it once across this way, once across this way, and once across this way. So you're looking for a worst case scenario. So we know the piston goes up, piston comes back, and the axis it pivots about or tries to pivot about is this piston pin. And when it does, it tries to tip this way at the top. When it goes the other direction, it tries to tip this way at the bottom. Where do you think on the piston, on the outside or the OD of this, outside diameter, where do you think you're gonna find the most wear? Think you're gonna find it in this area here, or are you gonna find it in this area here?
Top and bottom.
Top and bottom, exactly right, because this thing's gonna try to tip back and forth. The other thing is the rings fit in here. We'll talk about the rings in a minute. So the rings, every time you change direction, the rings still think they're going this way, but the piston's already started back this way. What happens to the width of these grooves? They start to spread a little bit, all right? So there's a check for that. If you look in your direct drive manual, there's a little picture in there with a ruler sitting on a table. You put the rings back on this thing. You put the ruler up this way or straight edge, and then you stick a feeler gauge in there. Everybody got a feeler gauge? You never need it. Go buy yourself one, cheap as hell, okay? Or a Napa or something. Get yourself a feeler gauge. Sears maybe. Sears doesn't have much in the store anymore. Now the top land might be smaller than the rest, but it might be bigger than the rest. So you can't really say one way or the other definitively. You can see this one here has 3 different size ring lands on it. So this one's the thickest. The next thickest is the next one down. The thinnest one is this one here. Then you go into the skirt of the piston. Okay, during the process of manufacturing, what they do is sometimes you'll look like somebody's been grinding inside here. If it's a cast piston, they'll get in there with a little grinder and cut the flashing off. So the flashing is the stuff that kind of squeezes between the molds. So you put a couple of molds in there, or the molds join, the aluminum tries to get between them. So they'll get in there and cut that material out. So you might see somebody's been inside there grinding.
So can you explain what cast flashing was? Is it just like little bits of aluminum or something that are left over from the cast?
Flashing, yeah. Flashing is, so you've seen this before. Any of these got some flashing on it? Most of them, they grind it out.
Is there a little overlap or something from the mold?
Yeah, it's where the molds join. This one's pretty close to flashing. So if you look down inside of it here, you'll see this is a 3-part mold on this. The 3 pieces of the mold are set in place, and then they cast the aluminum around it. So those lines that are around the inside there, those are could be construed as flashing. Okay. It's just places where the mold pieces fit together, and there's going to be a little bit of overlap in there, and that aluminum's going to get between them. Now they may be glass beaded or shot peened. And what that does, when you shot peen something, it creates a little pressure in the surface. So if you take a surface like this, There's all kind of little stresses can build up in the surface. So what they do is they spray it with shot, either lead or steel shot, but they can use glass beads. And what that does is those beads strike the surface. It's aluminum. It's going to leave an impact crater. And so what you're going to end up with is a surface that's like this. Okay? So the surface is going to have a microscopic finish on it. You actually see it. You don't need a microscope. So instead of having a nice flat surface, you're going to have this bead impacted surface. So any of you have ever seen an arched bridge? Have you seen an arched bridge, anybody? Okay, so just think of this as being an arched bridge upside down. What that does is that carries the load out this way across the surface. It spreads the load out instead of having everything concentrated in one spot on the surface. So you can actually make things stronger by putting impact craters in it. So the pistons, insofar as weight goes, should be within 5% of each other. And there are specifications in your book that talk about this. So you want the set of pistons to be fairly closely matched. If they're not, you end up with a vibration issue. Or you could. And so anything that rotates in the engine or moves, reciprocates, you want it pretty closely matched for weight. This goes for the connecting rods, and also the crankshaft itself should be fairly closely balanced. There was a guy, I'll tell you this little story real quick, we'll take a break. There was a guy, there's an AD note on the guy. He was a NASCAR guy, and he did a lot of work for NASCAR. So he would balance crankshafts, he would balance connecting rods, and he would balance piston sets. And so these things run at a very low imbalance. But what he was doing was, if he needed to grind something, he just hit it with a grinder and take material off of it. Okay, so that wasn't so bad. One of the other things he'd do, if he needed some more weight on it, he'd put a block of weld on it. He'd take the heat treat out of that spot, just slap it on there, put some weld on there, and grind it off. And in the worst case scenario, a couple cases, he took some crankshafts and actually welded some steel plates onto them, so that he could generate enough weight on the crankshaft to get them to run smoother. Right? So what he did was he got caught by the FAA at some point. He said, "You can't do that." He said, "Well, we do it all the time, right here in good old boy country." And it didn't play with the FAA, so there's an AD note out on him. And if you couldn't prove that he didn't work on your engine, everybody had to come along and say, I've got to take the engine apart to look to see if old Billy Bob had been inside. Right? So it was kind of a bad deal. Most people, if you had your engine overhauled within a reasonable amount of time, you had logbooks to verify that old Billy Bob didn't work on this thing. But know that guys do some crazy stuff inside these engines, and it can cost you or it can cost somebody a lot of money. So you're not allowed to weld on a crankshaft. These things are heat treated. Connecting rods, you're not allowed to modify these things. They're heat treated. Pistons, same thing. You're not allowed to modify those. So now that when you're doing an overhaul, you're taking parts out and putting new parts back in, and that's why you can do overhauls. So everybody in this room can do an engine overhaul once you have an A&P license. You don't have to have an inspection authorization. You don't have to do a 337. It's not required. But you do have to make a logbook entry stating that you use some publication as your authority to do the work. We do that. Everybody in this room could do an engine overhaul. It's not that big a deal. It's really very simple. So why don't you take 15 minutes, 2, 3, come back about